Hey there, man, Alejandro, and welcome back for day 108 of me doing the NeetCode 150 challenge. So today we're doing another LeetCode Medium 2D dynamic programming problem, and without further ado, let's get straight into it. Okay, today we get LeetCode Medium problem 97, interleaving string. Given strings S1, S2, and S3, find whether S3 is formed by an interleaving of S1 and S2. An interleaving of two strings S and T is a configuration where S and T are divided into N and M substrings respectively, such that S is equal to Okay. I see. A plus B is a concatenation of two strings A and B. So substrings. So right, so if you're gonna do substrings, it's fine. You can do any substrings and so on. So you can. It doesn't restrict the fact that you can, like substrings or subsequences and so on. At the end of the, or no, it is not subsequences. So you must always pick a new letter. Is that the case? Right, so you must exhaust everything. Right, I see, okay. So it's not subsequences, so you can't choose to like, oh, skip a letter and so on. No, you must pick a letter from the beginning of S1 or from the beginning of S2 for S3. And okay, the reason why DP is going to come in is like, you know, obviously if the same letter is available that you want for S3 from S1 and S2, then you'll do both cases and see if either one returns true. Okay, I get the gist of this problem. All right, this is not going to be too difficult. We'll have a self-dot. Ooh. But I was thinking of how to do this as a 3D dynamic programming problem. We want to do it as a 2D. Okay, we can first do it as a 3D. S2, self.S3. Interesting. So we want to do this. Or okay, I can kind of, it might be cubic. I might be able to do it in 2D with a for loop. Yeah, so it's 100, so 10 squared cubit. Yeah. So I might just be able to do a for loop around S3.length. Yeah, so okay. So instead of doing n cubed by having 3D and so on and having the index of S3 and like returning true if you're about to get to the end of S3, right? We can just do a for loop here. Or, okay, let's trust my gut here. Let's just do self. We'll do I, J, K. Or here we can do S1, S2, S3 index. S2 index, right? So the very beginning is return delta dp of 0, 0, 0, right? So at the very beginning, we'll have 3D dp. Here we'll do base case is here we can put a cache recorder, or we can do, you know, self.memo is equal to this and just do like, you know, if these three guys in self.memo return self.memo of these three guys. Okay, great. Otherwise, like, you know, you can put a cache creator if you're lazy like me sometimes. But here, just because we're in the NeetCode 150 dynamic programming section, I want to make sure that I do a good habit of using something like, you know, self.memo and so on, just to make it clear exactly what I'm doing and not using like Python libraries whenever I can avoid to do so. So yeah, so here we'll say if S3 index greater or equal to length of self.S3, then we found a valid permutation, turn true. Otherwise, it's like, you know, ooh. Oh, that's interesting. Can you solve it using only O of S2.length? Jeez. I see. So I gotta think of how to do it in cubed. Then I'll have to do n squared, and then they want O of n space, which is very interesting. Okay. I don't know if I'll be able to do that, but we want to at least be able to solve this problem inside 2D at some point, right? So this will be returned true. S1 letter, S2 letter, S3 letter, so self.S1 at S1 index, so the S2 at S2 index, tilde S3 at S3 index. Doesn't equal S1 letter. Doesn't equal S2 letter. False. Oh, as if it equals just the S1 letter. Then we'll do okay, for now, we'll just be lazy and we'll do a cache decorator. Okay, we'll put this up the memos afterwards. It's fine. Here, if it's equal to S1 letter, then return self.dp of S1 index plus 1, S2 index, S3 index plus 1. Otherwise, if return self.dp of an index, S2 index plus 1, 3 index plus 1. Otherwise, return this or this. Right, so I'd expect something like this to work. There's no attribute S1. You go to S1, S2, S3. Because something like this should work, right? S2, S3, S3, S2, S3, S2, S3, S2, S3. Okay, so that's accepted. Let's submit. Wrong answer. I'll put true. Wait, what? Return S1 index greater equal to length of self.S1 and S2 index greater equal to length of self.S2. Right, and so now this works. Okay, there we go. So we have a working solution, and it beats 57.17% of solutions, which is great. The only problem is that we have a 3D DP algorithm, which is very probably not what was expected. Although, okay, what I'm going to guess is that essentially the idea behind the problem is the same, just because I'm right at the dead center of this standard deviation curve. Okay. Okay, nice. So we at least know that we can solve the problem. So yeah, so it's very, very obvious, right? It's like the decision points are really going to come in when right, so the point is that essentially I have cubic subproblems and over 1 time per subproblem. So it's going to be the same efficiency. Sorry. There's just what I can do is essentially make a 2D DP and like do like, you know, ON work per subproblem and so on, and keep it the same and so on. Just like introduce for loops at places and there we go. Well, this is the most logical sense solution to me, though. Here, instead of using cache, we can probably use something like this. Equals this. Turn. Equals this. Turn. Right, so now we use like self.memo. And yeah, so it makes us even a little bit faster. You can even do equals this or this. Equals res, return res. Res equals res. Equals res. Res. Right. This might make us even faster. Maybe not. This might still work. Yeah, so we don't need the other AND cases. Really? Now you're telling me that it's slower. Okay, no. 37 ms beats 88.58% and so on. Like, I'm kind of tempted, to leave the solution this way, just because it's, like, so nice and efficient. It's so nice. Yeah, it's so... There you go. Like, this is clean. This is a clean solution. Just we really try to make it 2D just because it's a NeetCode 150 2D dynamic programming problem, right? So, okay. So in a situation like this, right? Here we'll call our DP, and we'll call it 3D, DP 3D. Right? If anything, we'll call it 3D DP. Ah, we can't do it. DP 3D. Right, and here it's like time complexity. Here we'll have O of length of S1 times length of S2 times length of S3 subproblems of so this is O of 1, 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 O of 1. 1 time per subproblem equals S2 times S3, where S1, S2 equals length of S2, S3 equals length of S3. There we go. So that's the overall runtime complexity is going to be the length of these strings multiplied together, right? And that's going to be the best way they can solve this problem. It's just that obviously, like, you know, it's just 3D DP with O1 time per work per subproblem. If you want to make it 2D DP, you can probably do so with the exact same logic, where it's just you have O of, let's say, S1 times S2 subproblems, and then O of S3 time per subproblem, or something like that, right? So essentially, it's like, you know, instead of having n cubed of 1 subproblems, you can have like n squared of n subproblems, right? And it's going to be the same type of complexity at the end, but that way you can essentially make it 2 DDP instead of 3 DDP and so on. But yeah. So yeah, the challenge is going to be figuring out how NeetCode wants this to be a 2 DDP problem, because the intuitive way for me to solve this is to just make it 3D, right? Just have an index for each one of S1, S2, and S3, and just roll through the 3 guys there, right? But yeah, this is going to require n cubed space. And so these guys are also saying that there's a way to do it as like of n subproblems. So there's a way to do it where you only keep track of S2's length. Is S2 like greater or equal to S1 always or something? No, not necessarily. That's interesting. So here we would want like a def dp2d self. And what would we want? Probably like S1 index and S2 index, right? So this follow-up kind of suggests to me that there's a way of doing this by only having the S2 index, which is kind of insane. Right, because how do you remember what the S1 and S2 index, where the S1 index is as well? Actually kind of unsure. Okay, I think this follow-up is actually really tough. If I have S1 and S2 index, that should be everything that I need, right? But is it? I also need to know the S3 index that I'm dealing with here. Also, I can try to do this as a bottom-up approach. Bottom-up approach. So here we'll have dp is equal to so here will be false times here we'll do S1, comma S2, S3 equals length of S1, length of S2, length of S3. Jeez. S3, range S2. Okay. Now I'll say dp of, so this will be S3 plus 1, S2 plus 1, this will be S1 plus 1. dp of S1 to S3 equals true. Now we'll do for S1 index in range S1 minus 1, negative 1, negative 1, for S2 index in range S2 minus 1, negative 1, negative 1, for S3 index in range S3 minus 1, negative 1, negative 1. We'll do case 1. Okay. So we now need to mimic things. So here we'll have S3 index. Continue. Keep as false. Otherwise, is false. This equals false. Case 1 equals case 2 equals dp of this, this, this. Now we'll say dp of one index, s2 index, s3 index, s1 or case 2. And here we'll say return dp of 0, 0, 0. Does this work? Not quite. Case 1, case 2, case 2. Don't set itself to false, but I don't think that's going to be the fix here, yeah. This is interesting, right? I do S1, S2, and S3 here. Same thing, yeah. So that's, turns out it's not enough. Yeah, this surprises me that this doesn't work. Yeah, it's not gonna matter the way that I do these things, right? Yeah, not at all. How come that bottom-up approach doesn't work? Oh, am I just not populating the bottom up in the appropriate order? S3 index should probably be first. This one gets moved no matter what. But now even with that, it's still wrong. Here we might be able to do some logical ideas in there. Right, where here I do something like this. Right. Maybe here I might be able to just loop over all the S, like, loop over all the S2 indices. I see. It's just gonna be tough. Yeah, it's gonna be tough. Doing this in 2D. For S2? Or even just bottom up in general. Yes, this is just not the right topological ordering. But again, it's because you're gonna zigzag between the two, so yeah. So it's just like what I have here is just not the right topological ordering. So the bottom-up approach is a little bit more convoluted. Again, the advantage of top-down is just like you never, ever, ever have to worry about these things. You just compute things as you need, and if you don't have them, you can compute them. If you do have them, then great, right? That's why I love caching and doing top-down DP, because you just never have to worry about, oh, what is the order of this, so on, blah, blah, blah. Yeah, it's because it's like, S3 index should definitely be the very first for loop for sure, but there's like, S1 and S2 is just like it starts getting messy in terms of which one goes next. So that's kind of bad. Where it's like you essentially need to do like you need to like dovetail through them, if anything. You probably need to dovetail through them. I didn't even pay attention to this. I didn't even read the NMSM constraint. Right, so it's like, yeah, if you split it off into these substrings and you know the order in which you're going to do it, then it's like you can kind of fill in the gaps with the other one, right? Right, so you'd have to think in terms of cutoff points. But you still need to know a previous index for the S1, which is just terrible. I'm like kind of tempted to just keep my 3D approach just because it's so nice and clean. Well, it's like it's almost like what I want to do. It just makes so much sense to just have 3 pointers. It makes so much sense. It makes so much sense. Which pointer do I remove? I either remove S3 or remove S1. S3 we've kind of signified as like kind of the most important. You need to know where along S3 you're at. You might be able to get away with something cheeky with bottom up. Also, yeah, okay, great. So my AirPod. There we go. Put that guy back in there. So yeah, just it's tricky. It's quite tricky. How we're gonna do that, and then they want like oh man. Spice. Yeah, the 3D approach completely makes sense. Bottom up, I'm not sure if we're gonna get this. So I'll just leave this instead of like a big string here. Oh, is that why? Ah, maybe my bottom-up approach is working. It's just that doing it this way is not correct. Uh-oh. Uh-oh. We're back in business, boys. Back in business. Back in business. Back in business. Alright, alright, alright. Okay, okay, okay. I see how it is. I see how it is. Maybe, maybe. It might be correct after all. Let's do it the same way. Not quite. Really now. Maybe we do something like this. Let's make it even safer. Maybe that's what we're missing, those initial cases. Ah, so that's what we're missing. Those big initial cases, right? So now... Wow, so that's actually much slower. Interesting. Wow, so that's actually very slow. So there's a lot of stuff that I'm repeating, really. But this is just you cut down to the chase. So now I need to figure out a way to merge the two, basically. Can I dovetail through S2 and S1? Damn, it's crazy how much slower the bottom-up approach is. Because I guess it's just like, I don't need to be... It's kind of like before where it's like we don't actually go over all the targets that we need to exhaust. So this is just like insane overkill. Jeez, 30 ms beats 98.78%. Like at this point, it's like, do we even do a 2D approach? Like, why? It's so fast. It's so good. It's such a good submission. Why waste your time? It's so good. Ah. We should try to figure out how to do this in 2D though. 2D. What we really should do is essentially choose whether or not to do a cutoff at an S1 or an S2. Right, or if anything, like, you know, just do S2. I think the 2D solution will be something like keep track of only the S2 lengths, S2 index, and like the cutoffs at which you did stuff. Right, because if you keep track of the S2 length and the cutoffs where you did things, and it's like up to this to figure out the rest, right? I'm not sure. I'm honestly kind of tempted to just leave it as my 3D DP solution because it's just like if we come up with a 2D DP solution, it's not going to be faster than this, right? It's just going to be a clever trick to use less space, that's it, but the time is not going to be faster. Do I write two separate 2D functions though? Permutation for every single pair of cutoff points. Just, I don't want to do what I did again in like partition equals subset sum, where it's like, yeah, I found a 1D DP solution. At least it ended up being faster, but it's like, you know, I had a perfectly fine 2D DP solution. Well, I guess I wouldn't say that like totally fine just because it was super slow. But here, like, you know, speed is not our issue, right? If this was a daily challenge, I'd step right here. I'd be like, oh, we found optimal solution. GG, let's go away, right? So in this case, it's like, you know, I feel less guilty about not finding a 2D way of doing this. Right, where it's just like you got to do O of N work over something else. Maybe the test cases aren't exhaustive, right? Because I feel like I don't know if this condition is enforced. Or is it just a convenient side effect that that's always how things are? Oh yeah, because yeah, no, this is just this is a convenience because like even if you grab one huge substring from S1, then you can only just append one more substring from S2 and so on because there's no more interleaving left for you to do it. So it's by nature of this will be a condition that happens by nature. Yeah, makes sense. So that's why we don't have a wrong solution. So I didn't misunderstand anything. But yeah. I don't know. It's like if we have a 2D solution, it's pretty much just gonna be the same idea. It's just that you abstract away something in a for loop instead of having it as an index, but it just makes things complicated for literally no reason. I guess the thing that can make in a for loop is S3 index because that one always advances forward, right? Where S1 and S2 index are always right, where it's like But no, because you want it to be part of the. It's just so. This is still 3DDP by technicality. Yeah, there feels like a way of essentially getting rid of the S3 indices, right? It's always S3 index plus 1. So what I'm thinking of is essentially you can keep track of a new table, right? You don't have to have S3 plus 1 tables. You can just keep track of 2 tables at a time, and that way you make things too deep. It's going to be one of those where you can bring down the space from O of n cubed to O of n squared. Because I only need, like, the table for S3 index and S3 index plus 1 at a time. So I just need 2 n squared tables at a time, not 1 n cubed table. So let's see if we can do something like that. It's weird because I had it as S3 plus 1. Now here what I want to do is instead of doing dp of s1 index and s2 index, we can do s3 index, which is going to be equal to dp new. This will be dp old of s1 index plus 1 s2 index. This is what I mean by converting it from n cubed to n squared space, and that makes it from 3D to 2D. Okay, it's gonna be one of those where actually it might be easier to fix the bottom up than it is to fix the top down. So this will be dp new of s1 index. This stuff, no s3 index now, is equal to dp, because yeah, like the point is we only have s3 index and s3 index plus 1 at a time and so on, so you might as well just keep a table for the s3 index part and the s3 index plus 1 part, and then for the next iteration, like, you know, reset the new dp table and so on. So like this is pretty clever. Plus 1, and then this will become, instead, this will be dp new, no s3 index, be old, and then once we're done, right, with these two for loops, we'll say update dp old to dp new. dp old equals dp new. Here we'll say dp old. No. Well, it works because of this. Otherwise, we'll get an index out of bounds error. But now let's see if this works. dp old. Yeah, so this works. This works. Okay, we made it from 3D to 2D. I don't care that it's slow. We made it 3D to 2D. So basically, so instead of having, like, you know, S3 many, S3 many, this is so genius. I am a genius. And yeah, okay, the follow-up, yeah, it's because if you dovetail through the elements, I think you're able to do it in just linear space. It's just that, like, yeah, I might be a little bit too lazy to write logic to dovetail and so on, blah, 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 right? But yeah, if you dovetail through the elements, I'm pretty sure you can probably answer the follow-up. It's just like that gets a little bit excessively annoying. Noise. So yeah, so basically the one I can get rid of is S3 index. But yeah, now doing it top down. Or you know what? I could say, hey, technically I have a 2D DP bottom up solution. I just have a faster top down 3D solution. But technically, in terms of, like, you know, 2D dynamic programming, hey, I wrote a 2D DP solution. Sue me. Okay. Here we'll say old. We'll just call this DP. Right? To DDP by realizing that only 2D is needed at a time. Okay. So this, by the way, is a trick that I always learned from Professor Vassos Hatzilakos at the University of Toronto. Essentially, it's like, you know, oftentimes you can reduce the space of a DP solution just by, like, you know, instead of, like, you know, having n cubed space, you can have, like, 2 n squared, like, you know, mappings and always update them as you go and so on. So that's what I did. But technically, now in terms of the space, you see, it's 2D. It's length of S2 times length of S1, right? The time complexity is still the same because I have a for loop for each of them, but Hey, now there's only there's only n squared space I'm dealing with at a time. It is n squared, it is 2 ddp. Nice. Right, because like the dimensional dp, it depends on like, the space that you're using. In my memo here, it's like, I have up to n cube space, but it doesn't matter, right? Here it's like, I have a bottom up approach. It's just, yeah, doing it top down might be a little bit annoying. Or it's like you have to recognize that you're using, maybe it's like you can override the value, but you should only override the values one at a time, right? Where it's like, you should have a Boolean flag, and so yeah, you can use like a Boolean flag and so on. That way it's like, it's really 2D. But yeah, at that point, it's like, I'd rather keep this solution, which is very nice and crisp, the way that it is, just because it's so nice and understandable, which is my fast solution. And then here it's like, I technically have a 2DDP bottom-up approach. So in terms of like, doing it the way that was expected of me, which is like, I needed to do a 2D dynamic programming solution. I did it. I have a 2D bottom-up. Sue me that it's slow. There we go, right? But I have an also more intuitive top-down 3D approach that also works. So this is very nice. Obviously, if I run the self.3D approach, it just happens to be faster, because at the end of the day, the amount of work will be the exact same thing, right? Here's just like, happens to be a bit slow. But yeah, if I resubmit a couple times, might be a little bit faster. Really? So now you're gonna tell me that's slow, eh? And why is that the case? Why is it so slow now? What? What? We were at 98%. What is this? This is rigged. Absolutely rigged. This is rigged. Rigged. Maybe if I remove the bottom-up approach, it's a bit happier. Just because there's not so much code. Yeah, so if I remove the bottom-up approach, it's happy because there's not like 10,000 millions of lines of code. What if I put them all as a comment? So yeah, it's still fast and so on. It's just like, there's a long string. I don't like that and so on, but it's fine. It's completely fine. So yeah, it just doesn't like the long string. Well, obviously, if I remove that, so if I remove the long string, it's much happier. Or not. Maybe it just needs one more resubmission. So yeah, it's just very bipolar, I guess, lol. 99.38%. Now that is crispy. That is very crispy. Okay. Okay, yeah, 99. See, sometimes more and more dimension be better, it'd just be better. Obviously, like, if you do it bottom up, not have to redo the work that you don't need to and so on, like, you'll get the most blazingly fast solution, because here I'm like using NQ space, but everything is like, like a hash map lookup call and so on, so it's just very nice and efficient. And you only do the things that you need, right? Whereas like, if there's work that needs to be done. Right, whereas like here I can probably be like, if an S2 index doesn't match. Right, okay, I wonder like, how do you dovetail? You want 0, 0, you want 0, 1, 1, 0. Yeah, it's just, yeah. I'm sure like, dovetailing probably, by the way, dovetailing just means like, it's just like, it's good for enumeration and so on, where it's just like, okay, if you think of an S2 and an S1 index, you do 0, 0, then 0, 1, then 1, 0, then 1, 1, then like that way it's like essentially you're always growing the two at the same time, instead of like, you know, going through all of one and going through all of the other, so that you can essentially make things a bit more efficient and so on. And then you can probably use that to essentially only hold linear space and so on. So my answer to the follow-up, I don't know if it's correct, but my idea would essentially be like use dovetailing to make the space linear, and that's pretty much it. Okay. So nevertheless, as always, in all my videos, I do a quick recap of how I will solve the problem. So for this one, essentially what I did is, this is just me, like, you know, showing we got a nice and efficient solution, which feels absolutely crispy. But otherwise, essentially what I did is, like, you're given two strings S1, S2, and S3. You want to find whether S3 is formed by an interleaving of S1 and S2. What does an interleaving mean? Well, what it means is essentially you want to split two strings S and T into a bunch of substrings that are concatenated together, obviously, to form S, as well as T, and essentially interleave them as follows, right? Have S1 plus T1 plus S2 plus T2, or like, you know, start with T1, then S2, S1, then T2, S2, and so on. A plus B is a concatenation of strings A and B, right? And so you want to know, can you interleave strings S1 and S2 to make S3? Now, the important thing to notice is that this says substrings and not subsequences, right? So there's not going to be any element of skipping letters and so on. Every single letter must be included, right? It must be like, you know, split S1 into the concatenation of substrings of S1, split S2 into concatenation of substrings of S2, and then start interleaving those substrings together to make S3, right? That's the point. You cannot skip a letter in S1. You cannot skip a letter in S2, right? So that's an extremely important part or detail of the problem that is important not to gloss over, right? And so the way that I did things is like, okay, well, I need to include every single index, right? Every single one. So I'm going to start off at index 0 of S1, index 0 of S2, and index 0 of S3. I'm going to look at the very first index of S3, and I'm going to ask myself, like, okay, let's look at an example like the very first one, right? S3, the very first character is A. I'm going to tell myself, okay, I know that I must use every single letter inside of S1, and I must use every single letter inside of S2. So the very first letter that I have in S3 is an A. So I'm going to have to use an A that is either in S1 or S2. Obviously, I start from index 0 of both of them, right? I can the next letter for both S1 and S2 that I must pick is index 0. I cannot start skipping letters. I cannot be like, okay, S2 doesn't have an A here, so like, you know, let me skip into C's until I get an A. No. We're going to need to end up exhausting every single character inside of S1 and every single character of S2. So the very first character of S3, I must either choose the first character of S1 or the first character of S2. In this case, it's very simple. The very first character is an A, S1 starts with an A, and S2 doesn't start with an A. We legitimately cannot start with the first character of S2. We must start with the first character of S1 if there is a solution. There still might not be. There might be, right? In this case, we see the output is true, so there will be a solution, right? But the point is like, okay, in this case, there's only one letter that you can choose, right? You must fill this A. You can only use the first character of S1 or S2. You must use the A. Now, once you've used up this A, then you've essentially used that up in S1, right? And now you set yourself up to like, okay, this is the remaining string of S1 that I can use, right? And then you can still pick like, you know, the next character from S1 or S2 because like, you know, if you pick the next character to be an A from S1, which will be the case here since there's two A's, it's like, okay, you can just say like, you know, this ended up being like your first substring and so on, or like, you know, if you, and you can continue, or like, you know, if you pick the first letter inside of S, then it's like, okay, then I had like, you know, this substring over here, I added this substring, so you end up interleaving exactly as you want, right? So you can essentially think of like you have an index starting at S1 at 0 initially, S2, which is 0 initially, and it's like always pick like, you know, next letter from either S1 or S2, right? Obviously, you also have an index for S3. So here I have my DP function. So self.S1, self.S2, self.S3 is equals S1, S2, S3. I have the self.memo, all classical. And I start from index 0 of S1, S2, and S3. So let's look at the DP3D of S1 index, S2 index, and S3 index, right? So in this case, it's like, okay, if it's already in my memo, return that result, right? That's classical, right? Okay. Otherwise, if S3 index is greater or equal to length of self.S3, that means I've essentially exhausted every single letter inside of S3, right? But remember, in order for a solution to be valid, I must have exhausted every single letter in S1 and every single letter in S2. So if I'm past like, you know, every single character in S3 and I've covered them all, then return true if and only if it is the case that I've exhausted every single letter in S1. So, you know, S1 index is greater or equal to the length of S1 and S2 index is greater or equal to the length of S2, right? Only return true if I've exhausted every single letter from both strings, right? That's the point. Otherwise, we'll grab the, like, you know, S1, S2, and S3 letters at their respective indices. Since we know S3 index is not greater or equal to length of self S3, we know that the index here is well defined. Otherwise, like, you know, if we're at the very end, we essentially want to say like, no character. So whenever we compare none to any like, character, it'll obviously be not equal, right? We're just making sure that this is some gibberish value, right? Since these are all letters of the lowercase English alphabet, we could do something like, semicolon, because we know that's not an English alphabet character. And then if we submit this, we'll see that we get a working solution anyways, right? So it can be anything, just to make sure that like, it's not a character. So as long as it's not like, a lowercase English letter, you're totally fine. It can be absolutely anything. So it's like here, I'm just giving a gibberish value of none, if we're already past the index. Otherwise, the actual letter itself for both S1. So that way we have S1, S2, and S3 letter. And in case S1 or S2 doesn't have a letter because we've exhausted the full string, we essentially give it a value of none to essentially denote that we cannot use this letter, right? Because we only are interested in using a letter that we need, right? For example, at the very beginning here, we'll need an A for S3. So we want to use an A, whether it comes from S1 or S2. So obviously, like, none will not be valid, right? So if we can't take something, it'll be from the other string. Okay. Now the very first thing that we're going to check is literally, okay, if S3's letter is not equal to the S1's letter, and if S3's letter is not equal to S2 letter, well, we can't use either letter at either index, right? So for example, imagine S3's first letter was an X, right? Well, this is not an X and this is not an X. It's just straight up false, right? You cannot use either letter, so we just return false, right? Otherwise, if it is the case that S3 letter doesn't equal S2 letter, well, since this condition isn't true, it must mean that, like, S3 letter is equal to S1 letter, right? And it's strictly not equal to S2 letter. So that means, like, if it's like not equal to S2 letter, as it is in this case, and it's only equal to S1 letter, then that means we must pick the letter from S1 to match with S3, right? So here we'll like advance the S1 index by 1. We'll advance the S3 index by 1, and we'll keep S2 index the same, right? And that's the result that we'll return, because that's the only thing that we can do. If it only matches with one of the string's letters, then we'll use that string's letter, right? And same thing for the other case, right? So it's like in this example, all the indices start off at 0, 0, 0. So like, we can draw this example right over here. So here we have this A, B, C, C. S2 is equal to D, B, B, C, A. And S3 is equal to A, A, D, B, B, C, D. We'll just copy this. All right. So the point is, like, here it's like, okay, I have this letter. This is the next letter I need to consider. I can either grab the first letter here or the first letter here. Well, only A is valid. So I'm going to grab the A from S1, right? So I advance the S1 index and I advance the S3 index, right? Until we've exhausted all of S3, right? That's kind of the point. Otherwise, if both of them are the same letter, right? Let's say that like S2 also started with an A. Then it's like I could either go the route where I choose to use the S2 letter, or I could go the route where I choose to use the S1 letter, right? So what will I do? I'll try both cases. I'll try the cases where I exhaust the S1 letter. So that's like, exhausting the S1 letter over here. Or I'll also try the case where I exhaust the S2 letter instead, right? So I'll try the case where I keep S1 index the same, I exhaust the S2 letter, and I exhaust the S3 letter, right? And that's kind of the point, right? At every single, I'll always keep track of the indices of S1, S2, and S3, starting with 0, 0, 0. And then I'll always ask myself, like, okay, I need to fill the letter for S3 index. I must either use the letter at S1 index or S2 index. If none of them are the letter, return false, right? That's what this check over here is. If only one of them is the letter, use that one. Or if both of them have the letter, then try the case where you use either or. Try the case where you use the letter from S1 and advance S1, or try the case where you use the letter from S2 and advance S2, right? So if you can use either, try both cases. If you can only use one of them, then you do only the case where you can use that only one of them. And if you can't use either, then the answer is just false, right? So that's kind of it. And then it's like, you just return if there was we catch a result every single time, return the result in any case. And then we just return, like, was it possible from the very beginning, true or false, right? Now, so hopefully that's going to make sense. Now, the only problem is that this is a 2D dynamic programming section, right? And we have a 3D DP solution. So we have, S1 times S2 times S3, many subproblems where S1 is equal to length of S1, S2 is equal to length of S2, S3 is equal to length of S3. So we have this many subproblems and O of 1 time per subproblem, but this is, three-dimensional. It's like, the length S1 index, S2 index, and S3 index, right? So one thing I did for fun is trying to write a bottom-up approach to this algorithm. Now, you'll realize that the bottom-up approach is actually very slow. If I do, here I'll have a comment, S1, S2, S3 is equal to true. So it's like, yeah. Before, essentially what I did is I wrote a three-dimensional version of my code. So here, if I uncomment this out, and essentially here, yeah, let me do this. This will stay the same. Yeah, so here I'll uncomment this out. Here I'll uncomment this out. Here I'll uncomment this out. Here I'll comment this out. And then return dp of 0, 0, 0. Okay, so this works, and we submit. Now, what we'll notice is that this happens to be very slow. My bottom-up approach is a working bottom-up approach. It's just very, very slow, 1750 ms, beats 5.39%, just because it's like, you know, I'm looping over every single possible, like, you know, triplet of indices and so on, when I can really skip them, which I get the benefit of by doing top-down, because, again, I'll only call, you know, the recursive calls to the things that I need the result from, so that's why I love top-down. You don't have to think about topological order, and it'll automatically just, you know, do the things that you need. Obviously, if you find out the exact things that you need, and then you do array-based indexing instead of, like, you know, pushing a bunch of functions and like, you know, using delta memo like this, the O of 1 stuff might be a little bit faster, but, like, you know, since it's O of 1 stuff and so on, I always love writing DP in terms of a top-down way, because it's like, you know, you end up like putting, like, you know, a safeguard on your foot so that you never actually shoot yourself with the foot whenever you do top-down. Anyways, what I did here is, like, you don't have to understand the code too much, but essentially, like, my DP is my self.memo. It's 3-dimensional, right? Length of S3, length of S2, length of S1. It's like, you know, a 3-dimensional array. Like, you know, I said, like, okay, when I have, like, you know, the length of each one, that'll be true, right? So that means, like, you know, if I'm able to reach the length of the end of S3 and I've used up to the end of S2 and S1, then that's a true case, right? I use every single character in S1, every single character in S2, and I'm at the end of S3, so, like, you know, that's my base case of true, right? Everything else is false initially. Then we're going to loop, like, you know, for every single S3 index, for every single S2 index, for every single S1 index, like, you know, do the same thing, right? If the S3 letter isn't equal to either the S1 letter or S3 letter, then we keep it as false, right? Everything is initialized to false, so here I just do continue. Otherwise, you like, if I can only use one of those letters, do the case where I use that letter. Same thing over here. And then it's like, okay, otherwise, if I can use both letters, use both letters, right? And so it's essentially the bottom-up way, the bottom-up version of the exact same code as my top-down here. So if you don't understand the top-down, this is the exact same thing, just bottom-up, using an array and so on, a 3-dimensional array. Now, the one thing that I realized is, like, hey, I'm looping over these S3 indices, right? So one thing I realized is whenever I use my DP here, right? Let's highlight over all the cases that I use DP, right? So here, well, first of all, we'll just comment this out. This is for the new one here, right? So here we don't need this. Every time I have a DP, so ignoring the comments, what we'll notice is this: I do DP of something with S3 index is equal to DP of something with S3 index plus 1. Here I do DP of something with S3 index is equal to something with S3 index plus 1. DP of something with S3 index is equal to DP of something with S3 index plus 1, or something with DP of S3 index plus 1. So I'm always using only two-dimensional subarrays inside of my 3D subarray, right? Where it's like inside of here, I essentially have, like, you know, a 3-dimensional array, but essentially I'm taking a 2-dimensional part of it and only using 2 of them at a time, right? So it's like here, it's like, you know, for every single S3 index, I'm only using, like, you know, DP, like, you know, for any possible S1 and S2, but I'm only doing so at S3 index and S3 index plus 1, right? So it's like here, it's like, you know, DP of S3 index. I'm essentially setting the new values at the S3 index column with the ones from S3 index plus 1, right? Because I'm iterating over S3 index columns backwards. But the point is that what I'm realizing is, like, hey, I'm only using 2 arrays at a time, right? So once I'm done with stuff that's stale, I don't need to have it in my memory anymore, right? And here we'll notice, like, you know, beats 5.31% memory. We're using cubic memory, which is pretty bad. But since I'm only using 2 2D copies at a time, what we can do is, like, hey, instead of having n cubed total memory, right, where it's like, you know, I have S3 many 2D subarrays, I can just say, hey, why don't I keep track of 2 2D subarrays at all times, right? Essentially a stale version and a new version. And once I update, you know, the new version using the stale data, then it's like, essentially I make, you know, the new stale data, the new version, and then use that for the next one and so on. So it's like, you know, since for S3 index, I always use the things that S3 index plus 1 and never anything else, I can just keep track of essentially a current DP with the S3 index plus 1 data, and then it's like, you know, have a DP new array, which is exactly what I have over here with the new data. And that way, I'm only ever at a time keeping track of, whatchamacallit, n squared total space, right? So make the problem 2D dynamic programming instead of 3D dynamic programming, just by making that tiny minute detail. So here, instead of having like, n cubed dp, I'm going to make it n squared dp. So that's how I make it from 3 dimensions to 2 dimensions, right? I only have 2-dimensional subproblems at a time, even though it's going to be 3 for loops at the end of the day, because again, like, you can't escape the time complexity, but you might be able to lower the space complexity, so turn it from 3D to 2D. And then here's like, okay, I have essentially my DP will always be stale data at the beginning. Obviously at the very beginning, it's like, based off the lengths of stuff. So it's like, length of S1 and S2. This currently maps like, to the length of S3 as well. So it'll be true. And then it's like, okay, we'll have a new array, and initially I'll just set everything as false, right? And but we're gonna use the values from here to essentially populate the new ones, right? So here we'll say, same thing, S3 letter, S2 letter, and S2 letter, and so on. But now instead of saying like, dp of this stuff with S3 index is equal to dp of this stuff with S3 index plus 1, we'll just say, okay, dp new, right, where we're gonna put the new data in of the same S1 and S2 indices is going to equal to the old dp at the same S1 index plus 1 and S2 index over here, right? We're essentially recognizing that we don't need cubic space, we only need 2 n squared, two two-dimensional subarrays at a time instead of 1 3-dimensional subarray array, right? Sorry, it's just use the same word over and over. But here's the same thing, right? I can comment this out and bring this in. So it's like dp of new at the same indices as here will be equal to the original the dp like old, but which I call dp at the S1 index and S2 index plus 1, right? S1 index and S2 index plus 1, right? I'm recognizing I don't need this third dimension. It's just completely useless, right? And here the same thing, right? I don't need this S3 index and then these S3 index plus 1 dimensions. I can just say, hey, dp of new is at S1 index and S2 index is equal to the current dp at S1 index plus 1, S2 index like I have it here, and S1 index, S2 index plus 1 as I have it here, right? And then it's like every single time that I do n squared work here, and I've essentially fully populated dp new, I set the current dp to that dp new with the new data for the next iteration of this S3 index for loop, right? And at the very end, whatever's inside of my DP, well, this is exactly what I'm going to return. So now I just have 2-dimensional objects. I'm just going to do 0, 0, which again is just the exact same thing. It's just recognizing that I only need 2-dimensional space at a time instead of 3-dimensional space. I can cut down on the space and bring the problem from 3-dimensional dynamic programming to 2-dimensional dynamic programming. So now we can see, okay, so we're at 1741 ms, 35 megabytes of memory. Let's see if by doing this, we've essentially enhanced both things, right? And so now we see like we've shoved off like, nearly like, 500 ms, and now we're like, we're using way less memory. We're using 18 megabytes instead of 35 megabytes, right? Still a lot of memory at the end of the day. But like, now we only deal with 2-dimensional space at a time. And so that is very, very, very good. And so hopefully, that makes sense. So that's how I was able to bring this from 3-dimensional dynamic programming to 2-dimensional dynamic programming, right? And so I want to keep my bottom-up solution, even though it's slow there, so that way I've technically done this problem in a 2D dynamic programming type of way, so I can check off the fact that this problem in a legitimate way, just a little bit cheesy. I just didn't want to think of how to do this in terms of top-down and 2D and so on, just because like, yeah, I'd have to put a Boolean flag and so on. It's just like a little bit too much work for no reason. And so, but that way, so like I have like, proof of like I was able to essentially find a 2D DP way of doing this, but I'll keep my 3D DP function just because to me it was way more intuitive. And not only is it way more intuitive, it happens to be a lot faster, right? Because I end up like, not doing work that I don't need to and so on, even though the worst case complexity between this and the other one are technically the same, right? It's just like, it's like short circuiting, right? So sometimes I short circuit whenever I need to, but in terms of technical worst case complexity, there is no difference between the bottom up and the top-down solution, right? It's just that like the top-down solution in general cases will end up being much faster, right? And here's like, we have like, 68.20%, but the point is like, it's just being angry about the fact that I have so much code here, but essentially if I delete all this code over here that it doesn't have to parse, then I think it's usually a little bit happier here. Yeah, so like, if we give it a couple gentle taps here just for it to be happy, like, yeah, now we're at 81.93% and so on. If we give it like, a few more, it might come over to the 90% and so on. But yeah, so it's like it keeps incrementing and so on. But it's like, yeah, it's just a little bit of the randomness of the LeetCode solutions. But I'll just submit it one more time where I have my bottom-up approach as well. That is O(n) squared. So yeah, 62.75%. Not a worry in the world. So yeah, so with the 3D DP solution, it works. But still, to essentially say that, hey, I was able to do this in 2D dynamic programming solution, even though this solution is slower, I have like, hey, here's an accepted by LeetCode 2D bottom-up approach that is slower, yes, but works, and it's 2D. So I technically not only did this LeetCode problem, I did it in a way that is acceptable in terms of the NeetCode 150 challenge. So that feels absolutely nice, epic, and awesome. So yeah, a little bit of cheesing, but technically, I'm still on with the challenge. I didn't use any help, didn't do anything, and so on, and I was able to come up with a 2D approach. So sometimes you get lucky in life. That is how it is. But hopefully that solution made sense. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye bye.